بسم الله الرحمن الرحيم. رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقه قولي. Welcome everyone. I'm starting this online meeting by the name of God. And this is Hanan Saadeh, Professor of Atomic and Molecular Physics at the University of Jordan. I am very honored to be your host in this scientific webinar, hosting our esteemed speaker, Professor Lund Laureate. To start with, opening remarks will be presented by LAMBDA active member Reem Saif. Reem, the floor is yours, and I will be moving the slides resonating with your talk. Please, Reem.
Yes. Welcome all. My name is Reem Saif. I'm honored to represent LAMBDA Physics Group at the University of Jordan. We are a group of physics enthusiasts initiated at the University of Jordan by Professor Hanan Saadeh since 2015, and we're proud to say these days we're celebrating 10 years of physics outreach and science popularization. In 10 years, LAMBDA Physics Group has played an active role in lifting the standards of outreach of physics in Jordan. This is evidenced through numerous outreach activities, public lectures, and webinars we organized on local and international levels. Throughout this journey, we've engaged the public with science, inspired ourselves and others, and had a lot of physics fun. In the years to come, our hope is to continue our mission of curiosity and passion for physics, and to expand LAMBDA's membership beyond the students of the University of Jordan to anyone interested in serving LAMBDA's noble mission. If you'd like to stay tuned about upcoming events, please subscribe to LAMBDA's email list. If you are interested in working with LAMBDA as an active member, please fill in the registration form. Today, we gladly join the worldwide celebration of the International Day of Light, May 16, honoring the first successful operation of the laser, and the International Year of Quantum Science and Technology, honoring 100 years since the Heisenberg uncertainty principle. It is a real pride to host Professor Lund Laureate in a webinar resonating with these global occasions celebrated at our university, in conjunction with two important milestones: the 60th anniversary of the School of Science and the 10th anniversary of the LAMBDA Physics Group at the University of Jordan. Now I'd like to hand the floor to Professor Hanan Saadeh, who will be introducing our esteemed guest speaker.
Thank you, Reem. So welcome everybody again, those who have just joined us. And in this brief introduction of our esteemed speaker, I am sure that many of us have already explored the impressive CV of Professor Lund Laureate, not only nowadays, but even since October 2023, when she was awarded the Nobel Prize. But briefly, I would say that her outstanding academic career can be summarized in these few lines. She got her PhD. She was born in Paris in 1958, and she studied there, and she spent the first 20 years of her life until she got her PhD in multiphoton ionization in 1986 from the University of Pierre and Marie Curie. And since then, she started a permanent position as a researcher at the French Atomic Energy Commission, and she remained there until 1995. In her early stage, she got the chance to spend postdoc visits in Sweden and other research institutes in the United States. Starting from 1995, she took a decisive, hard decision to relocate to Sweden and to start over again from scratch her career, but she excelled, and in 2 years, she was appointed as a full professor in atomic physics. And since then, she is leading a group in Attosecond experimental work of Attosecond physics. Of course, she is a member of several prestigious scientific academies, including the Royal Swedish Academy of Sciences, and she received several awards in physics, not to forget the Wolf Prize in 2022, and of course, the most important and prestigious award in the world, which is the Physics Nobel in Award in 2023. And when we introduce Anne Laurier, of course, we highlight the Nobel Prize in Physics. She got the Nobel Prize alongside with the co-laureates Pierre Agostini and Ferenc Krauss for their groundbreaking work in generating attosecond light pulses to study electron dynamics in matter. But that's not all. If the universe is a scientist by the last accomplished, it's not fair. We should go back in history and see what was behind this accomplishment. So introducing Anne Laurier as a Nobel laureate, introducing her as the fifth woman in history to be awarded the Nobel Prize is not enough. In what follows, I will make a less formal introduction to our esteemed guest. Anne Laurier, from a little girl in Paris into a Nobel laureate in Lund. In 1958, she was born in Paris, or Paris, and she was born for a family fond of science. Her father was an engineer, her mother was a school teacher, her grandfather was also an engineer. One night, around the midnight, the family woke this little girl, she was 10 years old, to watch the people walking on the surface of the moon for the first time. That was in 1969. But that's not all. I think also she was inspired in a way or another with this environment of her home city, Paris. I had the chance to visit the Eiffel Tower once in my life. It was like 12 years ago. And I noticed that there are 72 names of pioneering Frenchmen engraved on the first floor of the Eiffel Tower. I thought when I learned about the accomplishment of Anne Laurier that maybe one day she passed underneath the Eiffel Tower and decided that she will engrave her name somewhere else. She will engrave her name in the book of the Nobel laureates. As a child, she was impressed by her math school teacher, and later on, when she joined the university, she also loved most the quantum mechanics lecture and atomic physics courses, and she always praising her physics instructors at the university. And among those instructors, there were two Nobel laureates in physics. Not to forget Marie Curie, who was a role model for every scientist. What if this scientist was a woman like Anne Laurier? So Marie Curie played a role in her life, and she got a PhD in the university that carrying the names of Pierre and Marie Curie, which is nowadays is part of the Sorbonne University. I find some similarity between our guest today, who became a professor in Sweden, in Lund, and Marie Curie, who got her professorship succeeding her husband Pierre after his death. They both studied physics and math, and they both aspired to physics or to become teachers or researchers. Back to the early years of the little girl Anne Laurier, she was aspiring to be a teacher. She didn't think about being a researcher. And years after, when she got the call congratulating her of her accomplishment of Nobel Prize, she answered the call. You see the image that went viral in 2023 after the announcement of the Nobel Prize. She said, I am a little bit busy. I have a class of atomic physics. My students are waiting for me. There was no surprise that shortly after that, she got the biggest flower bouquet from the students. And I think it was the dearest flower bouquet to her heart. We cannot highlight Anne Laurier without highlighting the university where she has been working a professor and a research leader, Lund University. Lund University was established back to 1666, and it has been the home of excellence in science since centuries. And not to forget that it's the home of pioneers in atomic physics, such as Johannes Rydberg, and his students, Karl Mann, Seban, who got Nobel Prize in 1924 in X-ray spectroscopy. Yes, he was not a Lund professor, but he got his PhD from Lund University. So I believe that the roots of atomic physics started on this land, the land of Lund. If you go to explore the website of Lund University after the announcement of the Nobel Prize in 2023, they wrote like a roadmap of the physics prize of 2023, starting from 1990 up to the remarkable date 2023. I think they should go back a little earlier in time. They should highlight not only this mother of the high order harmonic generation, nowadays a professor in Lund University. They should start how she was in the past. In her past, she was an obstinate PhD student, and even when she noticed and observed the high order harmonic generation for the first time, she was advised by her mentor, why not to try something else? Why not to try something more promising, maybe? At that time, she was so obstinate, and she decided that she couldn't understand what happened. She needed to understand. She was driven by her curiosity, and she decided to continue in that exploration. Probably she felt she had an inner feeling at that time that maybe this would be her line for the decades to come, but I don't think that she was expecting that it will be also the road to be awarded the Nobel Prize. If we highlight Anne Laulier today, as she was confident that she would get something from this strange high-order generation she noticed in her experiment, we also cannot forget to highlight the father of laser, who is being celebrated today on the International Day of Light and every year on this day because of his pioneering work in laser. Theodore Maiman, when he invented the first operable laser, he also suffered from the skepticism of the scientific community. There was a big doubt about this laser. Will it be useful? Who will be using it? Now, even if you want to play a game, you use laser. Not only for science and technology, not only for basic research. So this is also a source of fond memories in the history of science to remember or to recall the achievement of the father of laser. And back again to the role model, Marie Curie, the godmother of radioactivity. Yes, radioactivity is a different field of physics, not related to what we are talking about today, but she paved the road for many scientists, men and women, to succeed, to be dedicated, and to chase their dreams. Marie Curie, when she discovered radium, no one knew at that time that it would be useful in hospitals, but she did that only for the sake of pure science. Later on, it was proved it's useful. And there are many scientists in this world believing in what Marie Curie believed. Science must be done for the beauty of science on the first point. Then it could be proved it's useful, but at least it could be useful enough if it's enriching the curiosity of researchers, of students, and also of scientists. Also, she believed that we cannot hope to build a better place without improving people, without improving individual, and I find this very resonating with our esteemed guest, who also believed that science is not only about machines. Science is nothing but about people who are researchers and also society. With this, I stop and I hand the mic to Professor Mahmoud El-Jagoub to present a featured welcome on behalf of the University of Jordan.
Thank you, Dr. Hanan. And I must thank you, and I thank the LAMBDA group for presenting such a great guest to this webinar, Professor Anne. Thank you, Professor Anne, for accepting this invitation. And dear Professor Anne, prospective participants, esteemed colleagues, and dear students, it is my great pleasure to welcome you all on behalf of the University of Jordan, which is the country's first largest university, to this webinar titled Attosecond Light Pulses for Studying Electron Dynamics. We are honored by your presence and deeply appreciate your participation. In fact, we are particularly delighted to see attendees joining us from across the globe. This does not surprise me with such a great guest. This diverse international presence also speaks volumes about the unifying and borderless nature of science. It is an exceptional privilege to welcome our distinguished guest, Professor Anne Lollier, recipient of the 2023 Nobel Prize in Physics. Professor Lollier, thank you for graciously accepting the invitation of the LAMBDA Physics Group and for joining us on this meaningful occasion, the International Day of Light in the International Year of Quantum Science and Technology. This year also holds special significance for us at the University of Jordan. We proudly celebrate the 60th anniversary of the School of Science and the 10th anniversary of the LAMBDA Physics Group. Both occasions milestones that underscore our deep commitment to advancing scientific education, research, and outreach. The School of Science remains at the forefront of promoting excellence in physics and beyond, and the LAMBDA Physics Group continues to play a vital role in fostering science communication and public engagement. Your talk today, Professor Lollier, aligns perfectly with these goals and inspires us all. In closing, I extend my heartfelt thanks once again to our guest speaker for sharing her pioneering work in attosecond physics. I also thank all our participants from Jordan and around the world for being part of this important event. Finally, I commend the LAMBDA Physics Group for their dedication and efforts in organizing this webinar. I wish you all a stimulating and fruitful session, and it is such a great pleasure and a great occasion to listen to a Nobel laureate like Professor Lollier. You are welcome, and thank you.
Thank you very much. It was really a very, very nice introduction. So should I start talking now, or yes?
Please go ahead.
I would like to share my screen. So you can see it?
Yes.
Yes. Okay. Okay, so I'm very happy to be with you. And again, I would like to thank you for the fantastic introduction. This is the nicest I have heard. And I'm very happy to also to acknowledge the International Year of Quantum Science and Technology, as well as the International Day of Light, 16th of May. And you will see I'm going to talk about light and as well as quantum science. So just to start, so this talk I will is both a little bit for the general public and for physicists. So I will mix up a little bit easy things and more physics results. So I start very simply by telling you what is an attosecond, 10 to minus 18 second, and this arrow of time goes from 10 to 18 second, roughly the age of the universe, down to 1 attosecond. And starting with some time scales for humanity, astronomical time scales. Once again is heartbeat, and then you have the mechanical time, electronics time scale for motion of atoms, and the time scale for motion of electron in atoms. In general, the lighter the particles, the faster they move. If you want to study the motion of atoms in molecules, you need to have femtosecond laser pulses. 1 femtosecond is 10 to minus 15 seconds. And this is an area of chemistry which is called femtosecond chemistry, which led to a Nobel Prize in chemistry to Ahmed Zival in 1999. If you want to capture electron motion, then we need attosecond light pulses. Atto is actually coming from the Danish language, atten, which means 18. So 1 attosecond is 10 to minus 18 seconds. And as was mentioned just before, the science of generating and using attosecond light pulses have been awarded Nobel Prize 2023 to Pierre Agostini, Ferenc Krauss, and myself. And in this talk, I'm going to tell you the background and the main steps of attosecond science. So this is the outline. First, a little bit of background. Then I will tell you about high-order harmonic generation, attosecond light pulse, and then a little of attosecond physics. I would like to start with the laser, of course, without which this research would not have been possible. And I'm happy to show also a picture of Theodor Meinmann and one of the first lasers, ruby lasers. And the invention of the laser is from 1960. It's based on the principle of light amplification by stimulated emission of radiation, which was discovered theoretically by Albert Einstein in 1916. And very important for this was the discovery by Max Planck in 1900 of the fact that the energy of the electromagnetic field was quantized, the photons. The invention of the laser opened new research fields. One of them is nonlinear optics, which started in 1961, right after the discovery of the laser. And here you have a description of the experiment showing for the first time second harmonic generation. So what you see on this plot is a laser, ruby laser, which is focused by a lens into a piece of quartz. The light is analyzed by a prism, and you have a photon detector, which was a photographic plate. And here you can see, of course, the laser, but also the second harmonic. And in this process, and the atom of quartz absorbs 2 photons from the laser and emit 1 photon at frequency 2 nu, if nu is the laser frequency. Another field that was open thanks to the invention of the laser was the study of atoms in strong laser fields. Very fundamental. It was simply, okay, we have atoms and we send a strong laser field. What happens to these atoms? They get ionized. You can detect ions or electrons. And my thesis work in the 80s, which was performed in France in this Commissariat Énergie Atomique, was the study of multiple ionization of atoms by multiphoton absorption. So now I'm coming to the second part of this talk, high-order harmonic generation. At that time, I was a young researcher at the Commissariat à Énergie Atomique in Saclay, close to Paris. So we had been studying the creation of ions and electrons by the light interaction of atoms with an intense laser pulse. So we had the idea that probably we also create excited atoms, excited ions, and it would be interesting to look at the emission from this excited species. So we set up an experiment looking very much like what I showed you at the beginning, but instead of a piece of quartz, we had a gas of atoms, a gas jet, and then we use a grating to analyze the radiation. What did we see? Well, we did not see fluorescence. We saw an unexpected result, and this was the formation of high-order harmonics of the laser. Here is a spectrum obtained in argon gas and showing many peaks, and the peaks correspond to a high-order harmonic of the laser field. For example, 31. This means that the frequency is equal to 31 times the laser frequency. You can only observe odd harmonics. This is due to a symmetry property of the interaction, symmetry relative to the origin. If you plot the distribution of these harmonics as a function of order, you see this characteristic behavior with first a decrease and then a plateau behavior and then a cutoff. And maybe the strongest surprise in these results was the fact that we had a plateau with many harmonics having the same or similar intensity. And this was surprising because at the time we were thinking very much in terms of perturbation theory, where the polarization in the medium is expanded in a series of powers of the laser electric field, and for a series not to diverge, you need the first order to be much stronger than the third, much stronger than the fifth, etc. And this was obviously not the case because we had this plateau behavior. If you look at the spectrum of these high-order harmonics, in which region of the electromagnetic spectrum are we? This is a picture of the electromagnetic spectrum. We start with infrared radiation, laser light, but you multiply by a high integer, and we end up in the region which is called extreme ultraviolet, above ultraviolet, below X-ray. And this is a region where, of course, the radiation is invisible to eye and also strongly absorbed by matter. So it's a strong interaction with matter. For those who are not at all in physics, let me make an analogy here between music and what we observed, interaction between atoms and laser. If you play a violin and you play a certain tone, you will get not only the frequency of the tone, but also many harmonics. And this is what is actually giving the clang of a music instrument. In both situations, we have a strong interaction between the string of the violin and the bow, or between atoms and the laser pulse, leading to the generation of these high-order harmonics. In the case of the music instrument, of course, we are talking about acoustic waves, and now I'm talking to you about light waves, so very different type of waves and different frequency, but similar phenomena. Now, if I want to be talk more about physics, what I found very fascinating in this process is that it's in the middle of two different fields of physics. The first one is quantum physics. How do you describe the interaction of an atom with a laser field? Well, you have to solve the Schrödinger equation that you see here. And in the right-hand term, you have the atomic potential and the laser atom interaction. In this case, we can describe the electric field as a classical field, and we can describe the laser atom interaction using the dipole approximation. But the difficulty in our problem is that this laser atom interaction is strong, comparable in magnitude to the atomic potential. But you also need to consider the response of an ensemble of atoms to the radiation. This is described by electromagnetism. And in order to have efficient high-order harmonic generation, you need all the waves which are emitted by all these atoms to be in phase, to be phase matched. And this is described by Maxwell's equation, which can be simplified in our case by a wave equation, as you can see here, where E is the generated field and P is the polarization of the medium due to this laser atom interaction. So in order to have harmonics, you need a strong single atom response, and then you need a phase matched many atom response. And as a young scientist, I liked very much these two aspects of this phenomena, and I still like it very much 40 years afterwards. In '92, I was a young scientist in France, and I was working with instrumentation and building, together with my first student here, Philippe Balcou, building dedicated instrument to study high-order harmonic generation. And this is the scheme of this instrument, including more or less the same things that I described previously. You have a lens that you can see here. The laser you don't see, it's behind the wall. There is a gas jet that you see here coming down. Then you have some optics to analyze the radiation, which is included in this vacuum chamber. So since the radiation that we produce is strongly absorbed by air, we need to work in vacuum, so we have pumps that are below that evacuate the air. So inside this chamber you have optics, and then you have a photon detector, which is here, and which is, in this case, an electron multiplier. This is the time where there was also a huge progress in laser technology, in particular with the invention of the chirp pulse amplification technique, which allows to amplify short and intense laser pulses, and which led to Nobel Prize to Gerard Mourou and Donna Strickland in 2018. And in Lund, they built a new laser facility using a new laser material, titanium sapphire, and this new technique. And you see a picture of this laser, and the titanium sapphire laser is amplifier is shown here. You see an orange light. So at this time, it was also beginning of European collaborations. Swedish people asked me to come with my instrument and my student, and to do experiments in using their new laser. And this laser was really fantastic to study high-order harmonic generation. And so we came to Lund, and what happened is I met my future husband in Lund, and 2 years later, I moved to Lund in 1994. And I became associate professor in 95 and professor in 97. So now I'm coming to the third part of this talk, Attosecond Light Pulses. The idea that high-order harmonic generation could lead to attosecond pulse was proposed by several scientists quite early, and the idea is shown on this slide. So here I'm representing 3 different harmonics, and let's assume that these harmonics are phase locked, which means the maxima coincide at a certain time. And here we have minima that coincide, maxima that coincide, etc. And the time scale between two of these lines is half the laser period. So let's sum these three waves, and you see that we get a series or a train of very short light pulses, light electric fields. And the reason is that when the three harmonics are in phase, then we have constructive interferences, while in the middle, when they are not in phase, you have destructive interferences. So the light is confined into rather short pulses. If you plot the intensity of these pulses, so this is the envelope square, then you get this series of light pulses. And now if you add not only 3 harmonics, but 10 harmonics, and if these 10 harmonics are phase locked, synchronized, then you will get even shorter pulses. This is an expression of Heisenberg principles, that if you have a broad bandwidth, you can get very short times. But the question was, are the harmonics phase locked? And it's going to take actually 14 years from the discovery of high order harmonic generation to the measurement of attosecond light pulse. An important step in this 14 years was a real progress in theoretical understanding in 1993 by Paul Corkum and Ken Kullander and co-workers, and also by Maciek Levenstein in 94. And this is called the three-step model. It's a very nice intuitive picture of the process, and it was formalized by a quantum mechanical theory by Levenstein. So this model is illustrated on this cartoon. So what is shown is an atomic potential, which is strongly deformed by the laser field, so that an electron in the ground state here can tunnel through the potential barrier, which is formed because of the laser field. So the laser field is strongly distorting this potential, making the wall increasing on one side, but decreasing on the other side. So now the electron in the ground state can tunnel through this potential barrier. Then the electron is driven away from the atom over several nanometers. Then the laser field change of sign, and the electron is brought back towards the atom. And then there is a certain probability that this electron recombines back to the ground state. So it's an interference process actually between what is left in the ground state and what has moved out and coming back. So in this recombination process, you have emission of a short light pulse with duration a few hundred attosecond. And this process is repeated every laser period, and actually even every half laser period on each side of the atom. And this is illustrated in this slide. What you have here on the left is a kind of a representation of what is happening as a function of time. So at a certain time, you have a emission of this electron coming back and recombining, leading to the emission of a short attosecond light pulse. And then a little bit later, you have on the other side, you have an electron that is tunneling, acquiring some kinetic energy and recombining, leading to another attosecond light pulse with actually a sign difference. And this is repeated. So you have the formation of an attosecond pulse train. So here we understand the physics of what is happening in the temporal domain. And now if you go to the frequency domain, the interference between these attosecond pulses will lead to a spectrum, a frequency com of high order harmonics of which odd orders. There was also a huge progress in understanding of the phase matching part of the interaction. Very simply, if you want to achieve phase matching so that the emission from all the atoms is phase matched, you need the phase velocity of the fundamental field, laser field, is equal to the phase velocity of the harmonic fields. Let's look at the variation of the refractive index with frequency. Well, you see that in the visible infrared region, the refractive index is usually larger than 1, while in this extreme ultraviolet region, it's less than 1. So if you look at this plot, then this means that phase matching is not possible. Fortunately, we also have partial ionization of the medium at the same time as we have high order harmonic generation. Some of the electrons that are emitted do not come back and simply leave. You have ionization. So because of that, you have a free electrons in the medium. And these free electrons lead to a reduction of the refractive index for the fundamental field, so that it becomes lower and actually lower than 1, and you can achieve phase matching when the two refractive index are close to each other. And this happens for a degree of ionization which is typically a few %. So on the one hand, you need a high laser intensity in order to generate high order harmonic generation, but the intensity should be not too high to ruin phase matching. So this phenomenon happens really within a certain window of laser intensity. Now I'm coming to a very important experiment performed by Pierre Agostini and his group, the first measurement of attosecond pulses in a train. And let me explain to you these measurements. This measurement uses a 2-photon ionization process, as shown here. So an atom is ionized by absorbing a harmonic plus a laser photon. And you can detect the electrons, and you will get a peak here. It's called main band due to absorption of the harmonic, and you get a sideband due to the absorption of an extra photons. The sideband can also be produced by absorbing the next harmonics, and then you have stimulated emission of a laser photon. This technique is called rabbit, which means reconstruction of attosecond beating by interference of 2-photon transition. So now we have a quantum mechanical process where you can reach a final state by 2 quantum paths. So the signal that you will get will be an interference signal and will depend on the relative phase of these 2 quantum paths. So on one path, you have the phase of the harmonic. On the other path, you have the higher harmonic. And you have also contribution from the laser, which we delay relative to the harmonic field by a time tau. So here you will have a phase omega tau. Omega is the laser frequency. And here you have a phase minus omega tau because it's an emission process. So that the signal will be an interference signal with the cosine term, which depends on the difference of phase omega tau plus phi q minus omega tau minus phi q plus 2. And this is really exactly what I'm looking for. I want to check how well synchronized the harmonics are. So what is the phase difference between two consecutive harmonics? How do we do such a measurement? Well, we need an attosecond interferometer, which is shown here. This is some kind of Mach-Zehnder interferometer. You split the laser into two. In one arm, you actually generate high order harmonics or a train of attosecond pulses, and then you filter the fundamental field here. So you are just left with this train of attosecond pulse. And then in the other arm, you have your probe pulse, and which is delayed with a variable delay stage. And you get, when you recombine the two radiation here, you get both an attosecond pulse train and a probe field with a delay tau, which can be varied. This interferometer needs to be very, very stable. You need to be stable over a few tenths of nanometers, and we use active stabilization to make it possible. And then you have electron spectroscopy. So you ionize a gas using this light, and you detect the electrons that are produced. For example, using, in our case, a magnetic bottle spectrometer. So what do you see? This is an example of so-called rabbit spectrograms. So what you have in color is an electron spectrum, and which is plotted as a function of the delay. What you see are lines corresponding to absorption of the harmonics. These are the main bands, or absorption of the harmonics plus or minus one laser photon. These are the side bands. With our laser, these side bands are separated by 3.1 electron volt. And now if you look at the function of the delay, you see that these peaks very nicely oscillate with periodicity, which is equal to half the laser period, 1.3 femtosecond. And this is our measurement. So going back to the experiment by Pierre Agostini, he did this measurement and measured the variation of the phase of the harmonic over the harmonic spectrum. These harmonics were not exactly synchronized, phase-locked. They showed a variation. However, this variation was not too important, and from this information and the intensities of the harmonics, he could reconstruct the attosecond pulse train, as you see here, with pulse duration of 250 attoseconds. Approximately at the same time, Ferencross and his group could not only measure attosecond pulses, but also generate a single attosecond pulse. And he did that by using very, very short laser pulses to begin with. Again, huge progress in laser technology with post-compression techniques. I'm not going to explain his measurement. The technique is called streaking, and is shown here. It's again electron spectroscopy, and from this measurement he could obtain pulse duration here of 250 attoseconds. So now I would like to finish these talks with a little bit of attosecond physics. This field is really exploding at the moment, going into many directions. So I chose to present only one example, actually related to quantum information and quantum physics in general. So this is first a picture of modern laboratory, for example, in Lund. The lasers that we are working with, they look like this. These are rather advanced laser where you want short laser pulses. This laser produces a laser pulse with duration 6 femtoseconds, very stable and rather intense. And as I said previously, we work with vacuum equipment to generate attosecond pulses and then use them in application. What do we try to do? Well, we are not trying to follow electrons rotating around the nucleus. This is a picture from the atom Bohr's atom model in 1913. But it's interesting to notice that in this model, the time for an electron to rotate around a nucleus is 150 attoseconds. No, we cannot do that because, as we have learned from quantum mechanics, these are waves, and you cannot, certainly not follow, watch the motion of electrons. But what we can do is measuring time for electrons to be emitted, for example, through photoionization, through the photoelectric effect, which was understood by Einstein and discovered by Hertz in 1887. And so this is a representation of the photoelectric effect for a simple atom. And the kinetic energy is equal to the laser photon energy minus, or light photon energy minus the ionization energy of the atom. Now, when Einstein understood the photoelectron effect, he was focusing on the quantum properties of light. Here we're looking at the properties of the photoelectron. Probably Einstein thought about the photoelectron as a particle which is emitted and goes to a detector measuring its energy, or maybe its momentum. But quantum mechanics, in particular Louis de Broglie, have also told us that particles are both waves and particles, and photoelectron is both a wave and a particle. And so the question is, can we measure the wave property of a photoelectron a little bit more generally? Can we measure the quantum properties of a photoelectron? And this is what we can do with our attosecond techniques. I will take a simple example, which is photoionization of helium atoms, which is the simplest atom with only 2 electrons. But in the vicinity of a discrete state, 2s2p states. So this is a beautiful example of quantum interference, quantum superposition, which was actually described theoretically by Ugo Fano in 1961. So here you can reach the continuum by 2 paths: direct photoionization or photoexcitation followed by autoionization, interaction here, which leads to 1 electron being emitted in the continuum. How do we access to the properties of the photoelectrons, not only its energy, but also its wave property, its phase? Well, we use the same Rabi technique. We use our quantum interferometer. And what we do is we make a copy of the photoelectron wave packet here, and we analyze the property of this wave packet using this quantum interferometer. And here is the result showing the amplitude of this photoelectron wave packet. And you see a beautiful interference effect close to this due to the presence of this discrete state. And we also show a pi phase variation across this resonance. So now we have the information on this wave packet, both in the amplitude and the phase. It's a little bit like in optics. We know the amplitude on the phase as a function of frequency or photon energy. We can go in the temporal domain, and we know we can deduce the amplitude and phase as a function of time. We can even do better. We can make what is called a time frequency representation of the electron wave packet. And this is what is shown here. This is a Wigner distribution in time and energy. And what is shown here is really the time evolution of this photoionization process. First, you have in priority, you have a direct photoionization leading to this big yellow feature. This is can be interpreted as a direct photoionization. This is a very fast process, broad in energy. Then you have a strong interference phenomena here. The blue part means that the Wigner function is strongly negative. So this shows interferences between the two quantum paths, this path and the path via the excitation to the 2s2p state. And finally, a little bit later in time, you have predominantly this photo-excitation process followed by autoionization. And this takes a longer time and it's more narrow in energy. Now, to conclude, I would like to take the next step in our investigation, which is, well, can we do better than that? Here we assume that our photoelectron is fully coherent, and it's a little bit very much like an optical wave, phase and amplitude. But maybe in some case, we lose coherence. Can we really measure the quantum state of a photoelectron? And this is what we have done recently using, again, a quantum interferometer using a probe field. This time we use two different frequencies of this probe field in order to probe different energy region of this photoelectron wave packet. Just to make you understand better how this works, let me split this XUV photons into two, part of course, the same XUV pulse. And here you see that we have, again, two paths, quantum paths, leading to the same final state. So if we study the electron here as a function of delay, you can get some information about the properties of the photoelectron wave packet. And in particular, this interference tell you whether there is a phase relationship between two different energies of the photoelectron wave packet. And this is what is called in the language of quantum physics coherences. So this is a signal that we study. Instead of 2 omega as before, it's delta omega, where delta omega is the difference between the two frequency of our probe field. What do we see? This is a picture of density matrix. So this measurement is, of course, repeated at different frequencies of the probe field, so we can scan the energy landscape of this photoelectron. So this is the type of measurement that we do in argon. So it's a density matrix. The diagonal is in this direction. And what we see is that this matrix is rather oval, is elongated. Obviously, we lose coherences in these regions. So it's not a density matrix of a pure state. It's a density matrix of a mixed state. And what is the reason for this? It's well, the reason is called entanglement, and in particular, in this case, entanglement between the ion and the electron, and it's due to the spin orbit splitting of the ion state. The argon ion can be left in the 2p1/2 state or 2p3 3 half states, so that the total wave function of the ion electron system can be written as is shown here. So we have again, because of this ion electron entanglement, in this measurement we are not measuring the degree of freedom of the ions, so we lose information, and this results in a mixed state and in this type of elongated density matrix. So this is a very interesting direction of this field of research at the moment, is to explore a little bit the quantum property of atoms, or in this type of photoionization processes. So with that, I would like to conclude this talk. Again, I was just trying to show you one direction. This field is going into many directions: molecular physics, chemistry, condensed matter, a little bit quantum, and also industrial application. But I think I have talked enough, and I would like to thank you very much for your attention, and also acknowledge my research group that you see here in Lund. And I would like to wish you all good luck, and thank you for your attention.
Thank you very much, Dr. Anne. Thank you for this insightful talk that highlights the seminal work behind the Nobel Prize in Physics 2023 and your current research on that. So now we open the floor for the audience for questions related to this presentation and to this field in science, attosecond or attosecond physics. So please, you can raise your hand, and then I can unmute you. I can see Sirine. Yes, Sirine. And please, the audience, once you take the chance to ask the question, you can shortly say your name, where are you from? Yes, Sirine? We can hear you. You are unmuted. No, we cannot hear you, Sirine. We cannot hear you. Okay, let's try another participant until you fix the problem of your mic. I cannot hear you, Sirine. Maybe you are logged in from 2 devices. Please check. Alia? Alia?
Hi, everybody. How are you?
Yes? You can go ahead with your question, please.
What personal difficulties did you encounter as a student while studying physics?
This is a difficult question. I as a student, I guess as a PhD student, it was a bit difficult to work only with men, which was my case. So that's one difficulty. But otherwise, I think of course, I had difficulties, but I think I've been lucky in my choosing this research area. So I had, I think things went very well for me.
Thank you, Dr. Anne. Thank you, Alia, for the question. But let's, for the first part of the session, let's open the questions about the attosecond physics and the presentation. Then we go through the personal journey and other scientific thoughts. So I will take another participant, Hadil.
Hello. Can you hear me?
Yes.
Yes, go ahead.
What are the current limitations of attosecond light pulse technology, and what do you see as the next breakthrough?
As the next what?
Breakthrough.
Breakthrough. Okay. I think one limitation is to go to higher energies, to higher photon energies, like in the X-ray. So this is clearly a limitation. It's possible to do that, but the number of photons that you get is very small. And fortunately, now you have attosecond pulses by free electron lasers, but this you can only get at some facilities, so it's not very easy. But there is always progress to be made. And at the moment, there is also a change in laser technology from titanium sapphire to ytterbium. And this is really much cheaper laser technology and also much, compact systems, easy to use. So things are all the time progressing. Future breakthrough, this is a difficult question. I think one challenge is to use these techniques to look at more complex matter, like big molecules, and then to understand the physics going on. So I think there are many breakthroughs in this direction waiting.
Thank you. Professor Sabih, Muhammad Sabih. Professor Sabih, you have raised your hand.
Hello, everybody.
Hi, Dr. Sabih.
Can you hear me?
Yes.
Yes, please go ahead. Yes.
Thank you for your nice presentation. I am Muhammad Sabayan from Iran, an atomic physicist that are working on attosecond light and also femtosecond laser. It is my proud to listen to your presentation. You are a scientist that I always mention you in my lecture and present your photo to my students, one of the biggest physicists in atomic physics. And it's a proud of me that I'm talking with you. I have some questions about the attosecond pulse generation. My question is that in theory, circular polarized light cannot generate HHG, high order harmonic generation, as Corcom model says that circular polarized light cannot. But in experiment, this light can generate HHG and also attosecond light. What is your opinion about this discrepancy? Do you believe in this discrepancy? Do you think the theory is correct?
I think the theory is correct. I think you are, if you generate harmonics with circular polarized light, you're probably not exactly circular polarized light, or you have a kind of strange, very strong regime, and it's a different type of process. This is what I think.
Yeah. Okay. Thank you. Then my second question is about the duration of emitting a photon of a frequency with electrons when electron is accelerating in the driving laser field. What is your opinion about the duration of emitting a photon when an electron is accelerated under the driving field? In fact, this phenomena is not instantaneous. It takes time to generate a photon. What is your opinion about the duration of emitting a photon or a harmonic when it starts, when electron starts to produce photon, and what is the end of this process?
Yeah, I think this is a difficult question. If you think about the recombination time, this is, I think, similar to photoionization, and this depends on really on the atomic system. But it's not instantaneous. I would like to say it's a few attoseconds, depending on the spectral region where you are. nothing is really instantaneous. Takes a little time.
So do you think this frequency has a width? Yeah, has a width in frequency domain, but and not exactly a precise frequency. It has a width. Yeah.
Yeah.
I'm correct. Yeah. Thank you. And last of my question is that do you know what is your opinion about the hot topic in attosecond fields? What fields in attosecond science is now working on, and if as a professor of physics wants to work in new and hot topics, which direction in these fields is hot? Do you think?
I think there are many hot directions, and as I said, a little bit more complex matter, molecules or biomolecules or materials. I think the direction towards quantum is also very fascinating, and also some people are starting to talk about the quantum property of the light, the harmonic light. So this is also very hot. So I think there are several directions which are very interesting.
Do you think we can work on quantum aspect of light in this regime? You know that the femtosecond laser pulse that derive this process is a high intensity or super high intensity. And do you think quantum light properties or quantum light theories can work on this field?
I think so. This is very new. You have to look at the literature. There are several ideas. There is no something very clear what one should do, but it's there are several ideas, mainly theoretical ideas so far.
Thank you very much. Thank you very much. Great.
Thank you, Professor Muhammad. Another question from the audience related to the physics of this presentation. Professor Nidal. Dr. Nidal. Okay, we take another one, but I saw that you raised your hand. Abdulrahman. Abdulrahman, you can go ahead with your question, please.
Thank you. Professor Lulia, we immensely appreciate you.
Hanan, sorry for the mic. I had to unmute it. Can I go on or what?
Yes, okay. You can go. You can go ahead. Yes.
Okay.
Sorry, Abdulrahman. I will come back to you.
Sorry, Abdulrahman. Bonjour, Madame Louye. Thank you very much for the interesting topic. Nidal Irshadat from the University of Jordan. I'm a professor of high energy physics, actually. Just one remark, actually two, but okay, I will be brief. And one question.
Yes.
The question. Finally, you are able to control the quantum tunneling, which is interesting. It is not fundamental, I know, but finally we are using this peculiar phenomenon, which is the tunneling in quantum physics. Can we do more of such control, or and what are the means to do that actually? This is the questions. Let me give you my remarks. It is very interesting. I noticed while listening to you, reading things about the subject, that the theory behind the whole thing is the one that we had since the 60s, actually. The main progress was in technology, was in our ability to construct powerful lasers and short signals lasers, etc., etc. This is very interesting that it is noticed. Number two, one of the most important applications, besides the applications you cited, is actually quantum computing. And now people are working on producing microprocessors which can execute operations in attoseconds, in hundreds of attoseconds actually, which will raise the speed of CPU to something like petahertz. We are not talking anymore of gigahertz. We are talking of petahertz. Thank you very much again. By the way, je suis actuellement à Paris, donc thank you.
Okay.
Thank you, Dr. Nidal. Yes, Dr.
Yeah, I think thank you for mentioning the application to petahertz electronics, but I haven't seen quantum computing as application. So if you know something, yeah, please let me know. But regarding the control of quantum tunneling and all of these things, I would like to say yes. It becomes very clear to me that what we are able to do is really control processes in atoms and molecules in a way which has never been done before, and this is just the beginning. So that is becoming more and more clear that we can measure really what is happening when light interacts with matter, and that means that we also gain control on what is happening. So it is very exciting. But a quantum computer I haven't seen, so I haven't heard. So let me know.
I will.
Yeah.
Thank you. Back to Abdulrahman. Abdulrahman.
Yes, Professor Lullier, we immensely appreciate you joining us for today. I have found your presentation greatly valuable and perhaps inspiring too. I'm still taking quantum mechanics, so I would love to ask you if there are some theoretical limitations or perhaps experimental limitations for how short light pulses could be.
It is a very good question. The record at the moment is 43 attoseconds. I don't think there is a fundamental limitation to go shorter, because I mean, as I explained, you need to have a very large bandwidth. For example, many harmonics, and this is possible. But we don't know how to make all of these bandwidths to be phase locked, to be synchronized. So it's more a technological limitation as I see it. So I'm convinced that we will see a shorter pulses in the future.
Thank you. Thanks, Abdulrahman. Is there any other question related to physics? ولاء التميمي, Dr. Wala.
Yes. Good
You are
afternoon.
unmuted. Yes, good afternoon.
Yeah,
Good
please.
afternoon.
So this is Dr. Wala Al-Tamimi. I'm an experimental nuclear physics with a background in laser spectroscopy and of exotic nuclei. So my question, honestly, is about, like, do you think that could attosecond pulse techniques be adapted to probe transit changes in hyperfine structure during like ultra-fast electron dynamics, especially in exotic or short-lived nuclei?
This is a really tough question. Hyperfine structure, no, I don't think so. But because we are even if we can have a higher spectral resolution by using tricks like, 2 pulse, things like that, this would require very, very high spectral resolution. Transition in nuclei, possibly, I don't know enough, but I would. This would be very, very interesting. Yeah.
Like, I mean, sorry, it's like the new techniques in like laser spectroscopy, like switching and pulsing lasers. Could that also like help? Also, like the continuous discovery of like the attosecond and like the techniques in attosecond.
Yes, I think yes. I think there are many new things to do. So yeah, the field is quite open. This Nobel Prize is happened after 40 years of studies, but sometimes Nobel Prize means that they kind of the field is kind of finished. You know everything, But in this case, I think it's really means that, okay, now you can really have a new tools, and you can further develop the techniques and the physics.
Yeah, thank you.
Thank you. I can still see raised hands. Hadil, do you still have a question, Hadil? Hadil?
Yes, I have another question.
Yes, please. Hadil is a
Honestly,
bachelor student in my class of optics. Hadil Shakhambe, right?
yes, right.
Yes, Hadil is an undergraduate student in the course of optics. Yes, go ahead, Hadil.
First, I know what is the difference between femtosecond and attosecond, but actually, how do attosecond pulses enhance our understanding of ultra-fast electron dynamics compared to femtosecond techniques?
I think it's both that these are short pulses, and also that these are pulses which are in the extreme ultraviolet, so rather high photon energy. And this is the photon energy you need to do photoionization, for example. So it's a combination of high photon energy and short timescales.
Okay, thank you.
Thank you, Hadil. I kindly ask those who have already asked their questions to lower their hands so I can recognize new participants. Yes, Alia? Yes, Alia? Please.
Hi.
Yes, Alia. We don't hear you, Alia. Please unmute yourself.
Professor Annie, would you kindly share a special message to LAMBDA Physics Group on its 10-year anniversary?
Yeah, with this question, I think if we don't have more questions about physics, let's go to the second part of our session. That's general dialogue with our esteemed guests. So let's start with this request from LAMBDA Physics Group. What a message that you could share for the aspiring members of LAMBDA Physics Group in its 10th anniversary.
I'm quite impressed by this group, and I'm impressed by the fact it's your 10th anniversary. So I would really encourage you to continue to meet and to discuss physics, and to inspire, especially young women, but young people in general, to study physics.
Thank you. So other questions related to physics outreach, to scientific journey, to scientific vision of our esteemed guest?
Can I ask my question?
Yes.
Excuse me that I'm asking question for second time. Professor.
Okay, go ahead, Muhammad.
Yeah. What's your opinion about the femtosecond pulses? Do you think with HHG process we can go toward generating femtosecond pulses, or we need a new theory or new experiment? What do you think? Thank you.
I think that it's possible to get shorter pulses using high-order harmonic generation. I don't know if it's down to the zeptosecond, but certainly a few attosecond or even below. But the difficulty is to synchronize all the frequency components that you need. So it's again, it's a technological limit at the moment. But I don't think there are many people working on that, because the field is going towards applications of attosecond pulse, not to break new records. So talking to all the young people here, if you are interested to go toward shorter pulse, I think this part is quite open.
Thank you very much.
Thank you. Who else, please? Reem? Yes, Reem? Go ahead.
Yes, when you were asked about the challenges, you talked about being the only woman working with in a male-dominated field. Can you elaborate on struggles or challenges that are unique to a woman in a highly precise and male-dominated field?
I think one of the challenges, sometimes you feel quite lonely. So it's a bit more difficult to go through difficulties. So that's one challenge. At the same time, you are also more visible. So there are a little bit both aspects. But I remember when I got my first PhD student, that was a woman. This was in 96. So it's really 16 years after I started. This was really such a pleasure to work with a woman for the first time. Then I got my first postdoc woman, and this was in 2002. But now my research group, if you remember my last picture, it's about 30% women. So I think that the situation is really changing, at least in Europe, that there are more and more women doing physics.
Thank you. I have a small follow-up. Being a woman and succeeding in this field, people can sometimes look at you as if you represent all women in physics. As a woman, like, your success is the success of all women, and any failure is the failure of all women in the field. Do you find that pressure or extra responsibility to be maybe a good thing, or can be used for good, or is it, a negative thing?
I certainly feel the responsibility, and especially since I got a Nobel Prize, I feel very strongly the responsibility to be a little role model for women in that wants to study science topics. Yes, it's a little bit heavy sometimes. It's both interesting and I think I should respond to questions and give talks but so I absolutely, but I also feel the responsibility. Let's put it this way.
Thank you.
Thank you, Reem. Thank you for raising this point. I would follow up also after what the question was raised by Reem. Have you faced like the challenge that being considered or accomplishing something, they always respond to that, oh, because she is a woman, she got the Nobel Prize. Because she's a woman, she got the World Prize. Have you faced such kind of challenge?
Very much.
Not reflecting on your capability. They don't say because she's excellent. They say, because she's a woman.
Yes, I have.
So
yes, absolutely. Especially like 10, 20 years ago, I got some grant. Oh, this is because I can tell you a story. I got one of these, the first call of a European Research Council grant. I got a grant and people told me, oh, this is because you are a woman. And I believe that, actually. I thought, oh, maybe they are right. They need to, this is a European Union. They need to have many women. And so maybe yes, I was lucky because I am a woman. And I believe that during many, many years. But then I was asked to be now on the other side, to be an evaluator of these grants and to be in a panel of ERC. And I saw how it works and how they are so very careful and so very professional that this is only based on excellence. So to me, it was a relief. Oh, but
Yes,
I had not
it's
gotten
a
this
stereotype.
because but it took me a few years to understand that. So yes, this is something I had to fight during my whole career.
Yeah, thank you for this explanation, because I think we female scientists, we face this day by day. We always face this. So it's
Yeah.
good to reflect on that as a member in the jury committees of these research grants, that it is highly professional. It's only based on excellence, on the
Yeah.
merit of science,
Yeah.
not the gender of the scientist.
Yeah, at least for those grants. So I think you need to build a confidence as a woman that what you do is good and not listen too much to this type of comments.
Yeah. Thank you, Dr. Anne. Thank you, Reem. Another question from Serene. Serene, if you can open your mic now, please. Serene. Don't you hear us, Serene? Okay. Other questions? Alia again. Serene, you are here. Please open your mic. No. You need to log out and log in again, or disconnect from two devices. I can see that you are connected from two devices. Okay, Alia?
Hi.
Yes, Alia.
Some research argue the scientific outreach is not essential. As a physicist with a broad impact, how do you view the importance of outreach in science?
I think outreach is important, and I think it's becoming increasingly important because now there are a little bit criticism about science, and so it's very important that the scientists are actually talking to other people and talk about science. So I think outreach is important, and I'm doing a lot of outreach at the moment as Nobel Prize laureate. This is almost a second job I'm doing outreach.
Thank you.
Thank you. Abbas. Abbas Majidi. Abbas, you raised your hand. Can you please open your mic?
Thank you. Could you hear me?
Yes, Abbas. Where are you from?
Thank you, thank you, Professor Laureate. I'm from Iran, Tehran University. I have a question, and my question is, always people consider the electromagnetic wave as a classical form. Why they don't consider electromagnetic wave as a quantization field and quantum optical phenomenon? Could we find more information about this phenomenon if we consider quantum as a fully quantum optics phenomenon?
I would say that until 5 years ago, I would have replied that but you don't need to quantize the electromagnetic field in our processes because it's laser fields and many photons and coherent states of light. So this is not needed. However, since like the last 5 years, this aspect is coming up very, very strongly. In particular, if you generate harmonics in materials, not in gas, but in materials, and where you have strong correlation, then you can get fields which cannot be described classically. So it's coming up very strongly now, this quantum optics part.
Thank you, Professor Lovier.
Thank you. Other questions, please? Abdulrahman, do you have another question?
Yes, please. Professor Lulia, excuse me for a long question. I believe one must acknowledge that they only meet such an esteemed figure, a scientist, few special times in their lifetime. So, if I may, I would love to ask you about the very first steps in your life when you were a student in our age. I have read much about Eugenie, and I did notice that you were awarded, in fact, a double master's degree in theoretical physics as in mathematics. So I would love to ask you what inspired you to join those two realms, and if you have any advice for someone who wishes to pursue the path of theoretical physics, especially that you have excelled and became perhaps one of the most influential pioneers in experimental physics after that you have once pursued theoretical path. I'm sorry for the long question, and I would love to thank you once again.
Thank you. First of all, I know it's different in different countries, but I studied in France, and it's not experimental and theoretical physics, it's physics. But it's true that I have a double master degree in physics and in mathematics, and actually I have a teaching degree in mathematics. And the reason is that at that time it was a choice between physics and chemistry or mathematics and physics. And I didn't like chemistry too much, and I liked mathematics very much. So I studied mathematics and physics, and also I think I wanted to do physics from the beginning, but I had this idea that it's very good to have a good, mathematical baggage, to have a good mathematical knowledge if you want to do good physics. So that's why I did that. I don't think I was thinking too deeply. I liked mathematics, and also the other reason is that I wasn't sure that I could do research, that I was good enough to do research, and if I could not do research or become, professor at the university, then yeah, I'm happy to be professor in high schools, and I thought I liked better to be professor in mathematics than professor in physics at high school. But then I became professor in physics at university. Yeah, this is personal story, but.
Thank you so much, Professor.
This session now, this part of the session is totally about personal stories and personal perspective. You reminded me again of Marie Curie, because also she had double degrees, but not double master. She had double bachelor degree in physics and mathematics. And she was the topmost student in physics and the second topmost student in math. So
yeah, I heard that recently, actually. I didn't know that. I heard that 2 weeks ago. It was very surprising.
Yes, yeah. She had double degrees in math and physics. Yes, yes. Other questions? I looked at the chat and I found a question in the chat from Nadia. Nadia says, "What message would you give to men fellow in your field?"
Can you repeat?
What message would you give to men fellows in your field? To men researchers, colleagues.
To the colleagues.
The question. Yes, to men colleagues. She's following up on the question raised by Reem.
Yeah, I think the main message is that this field is extremely open, and actually now it's impossible to follow everything that is happening, and just pick up one of the direction. Quantum is one direction. Application in industry is one direction, and application to chemistry. Yeah.
Sorry, the question was, what message would you give to men fellows?
To men fellows.
Yes, to men fellows in your field. Yes.
Yeah.
She's following
okay.
up the previous question. Yes.
But being a woman or a man in the, yeah, I think,
Yes.
okay, I can say one thing. My experience is that a research group is working much better if it's both men and women. And if there is also diversity, people from different backgrounds and with different competences. This I have seen many, many times. So my message to men would be, yeah, be aware that there are women that want to start to try to have a group which is diverse and try to help. I think if in a situation where there are many men and a few women, these few women, they need support.
Thank you. I can see 5 raised hands. Dr. Nidal, do you have another question? Dr. Nidal? Okay.
Do you hear me now?
Yes, go ahead, please.
No, actually, did you see my hand raised? Because I did not raise my hand.
Yes, it's still raised. Okay, no problem.
Okay, maybe I should unraise it. Anyway, no. Again, thank you, Madame Louillier, for this very interesting webinar, and wish you the best of luck in your forthcoming research. Thank you again. I will unraise my hand.
Thank you. Tala? Yes, Tala?
Yes. Were you able
Tala.
difficulty?
Sorry, Tala. Can you repeat the question?
Are you able to enjoy physics instead of focusing on its difficulty?
Okay. Were you able to enjoy physics on your journey?
Yes,
of focusing on difficulties?
Yes, for me to do physics has always been a pleasure and almost a relief compared to difficulties you can have in life. So it's a passion. I don't know if I answer your question or not, but yes.
I would say this is a typical question. We always we have been always asked about what got you into physics, what got you into science. There are many reasons, but there is no one unique reason I would say that it drawn many of us into physics or into science. But maybe one word can summarize everything when you say it's the love of this field, it's passion.
Yeah, and I must say I was very much I had a good family with people doing science and encouraging me. So I was very interested as a very young girl towards science.
Thank you. But also commenting on that, now 2 questions have been raised about why did you study physics or why you are passionate about science. Do you think that passion is enough for a researcher or for a student to follow up in this journey?
I think passion is important. I think another important thing is to be obstinate and to perseverant. That is also important.
To not
of course, you need to be a little bit good at what you are doing, But this is coming to, I mean, this is go together with to like what you are doing, I think.
Thank you. Muhammad Mahmoud.
Can you hear me?
Yes, please.
Yes.
Muhammad, undergraduate student.
Yes. Firstly, I want to thank you, Professor Lollier, for this interesting webinar. My question is back to when you were a student. Did you have the feelings and the thoughts of like, maybe I'm not good enough to be a theoretical or experimental physicist? And if you do, how did you face these thoughts?
I absolutely had these thoughts quite a long time, and this my so this is why I actually got a teaching degree in mathematics, because I thought I wanted to be a teacher. So I thought that if I'm not good enough to, or if I am unlucky, I will teach the young children. So this was my thinking. But then maybe I was lucky. I got a PhD position, and after that a permanent position, and then I moved country, and it was not easy all the time, but I managed to get a position. Yeah.
Okay, thank you.
Thank you.
Thank you, Muhammad. Farah. Farah Hani. Yes, Farah. Farah.
Hi, Doctor.
Farah.
Hi, Doctor. Yes.
Yes, please. Do you have a question? You raised your hand.
Yes. Throughout your long career in physics, how did you deal with moments of doubt or scientific frustration, and what motivated you to keep going when results were uncertain or unclear?
I think I already answered this, and my answer is both passion and perseverance. And also another thing which I haven't said is that I like to do experiment, but sometimes I like to do theory. So when the laser doesn't work, I do some theory or something like that. Try to do a little bit of both, to have not only one thing and then something is not working, but to have several things in parallel.
Thanks, Professor.
Thank you, Farah. Sireen or Reem?
Yes, this talk about experimental physics versus theoretical physics, it brings out the idea that a lot of theoretical physicists actually don't get the recognition that they deserve during their time. But more generally, I want to ask you if there are any scientists that you think deserve a Nobel Prize and never got one. And is there anyone specific that you think deserve more recognition during their lifetime or a Nobel Prize?
I would like to say that I'm certainly not going to give you any name, but the Nobel Prize is not about being a good scientist. The Nobel Prize is about making a discovery, which is useful for humanity. So of course there are many extremely good scientists that don't get the Nobel Prize for various reasons. You need to be a little bit lucky get a Nobel Prize is really you can associate your name to a certain discovery. So absolutely, great scientists never get the Nobel Prize, unfortunately.
Thank you.
Thank you, Riem. Following up on that, Dr. Ann, do you think that scientists should aim for a Nobel Prize?
Absolutely not.
So,
no,
to what they aim?
So it is not about getting a gold medal when you spring faster than anyone else. It's again to be a little bit lucky and to have been part of something which is useful for humanity and really new. So I don't think a scientist should aim to get a Nobel Prize. A scientist should aim to do good research, and also to educate people and to mentor young people. I think that's the aim of a good scientist.
Following the same line of Nobel Prize, I am wondering whether the Nobel Prize has changed your life since October 23 up to now. I still remember when I read about Marie Curie, she said, this prize ruined our life. Because of fame, we cannot do our personal life as we used to do it before. So I'm wondering, what about you? After the Nobel Prize, is Anne before the Nobel Prize like Anne after the Nobel Prize? What has changed in your personal life?
I think
did you suffer from this fame?
Yeah, I think that my life has changed absolutely because the Nobel Prize is really special. And I think it's much more now than when Marie Curie got the prize, because this was the beginning. But I would like to say that my job has changed. Now I'm doing outreach, I am giving lectures. So my job has changed, but my personal life has not changed. At least I'm trying not to. I'm happy with my family, my husband, and I absolutely don't want to change my private life.
How do you keep that balance?
Well, fortunately, my children are adults, so they are not living with us, and I have a husband that understands what is happening to me, but I'm trying very hard to keep normal life.
So, other questions from the audience? Abbas? Abbas, do you have another question? Okay, Hadil.
Yes, I have. Professor Laureate, how did your childhood environment influence your passion for science? And do you believe that can affect a person's desire to learn? Because I wrote about your life, especially childhood. So to me, I saw your childhood very amazing to love learning physics. And how did you come to realize that quantum physics was the field of physics you wanted to pursue in your future or career?
I think again I was lucky to be in a good family that didn't make a difference between girls and boys, for example, for their choice in life. So I'm very grateful to my late parents that they were a supporter. They were not pushing me, but they were accepting my choice and not making bad comments. So this was very, very good for me. Then I don't remember the second part of your question, but
how you got fascinated about quantum mechanics in particular?
Yeah, the quantum mechanics. I would like to stress the importance of good teachers. This is so important, and I have had good teachers in mathematics at high school, at the end of high school, and also in physics, and in particular in quantum physics. So they have, you know, when I was, I don't know, 20 or something like that, I thought astrophysics was really interesting. But then when I had these courses in quantum physics, I thought, oh, this is really exactly what I want to do. So teachers.
Teachers.
Yes.
Thank you. I don't see more raised hands, but I still have a few questions that I think we have to raise before we close. As a researcher now, away from teaching, as a researcher, as an experimentalist, of course, I did not, when I introduced you, I did not go through the H-index, the Google Scholar, the number of citations, which are impressively high for sure. I wanted to ask you your personal perspective about these calibers to measure science production. Do these metrics reflect really the true value of science? What do you think about each index? What do you think about number of citations for a scientist? I would like to hear from you.
Yeah, I think the number of citation is it says something more than H-index or number of publications, but the number of citations, I think it's because it really says which impact you have in your field of research. But one should be very careful because these numbers are so much field dependent. So one has to be very, very, very careful how to to use these numbers. Maybe what is most important is kind of the reputation you can have in your field of research, and I don't know. This is very difficult to evaluate researchers.
And what about each index?
In general. I don't know. I don't want to comment. It's again, it's very much.
Okay.
It's very much field dependence. Yeah.
Okay. Okay. And do you still have dreams as a scientist? Now, I think, I mean, as a scientist, do you still have dreams?
Dreams? Yes, yes, I still have dreams. Well, I always have. I'm very excited about the research that we are doing. Maybe I have one dream also is to understand better quantum physics using our techniques. One other dream is to see that these high harmonics are really useful for our society, like for making computers or things like that. And another dream I have, which is much more concrete, I'm trying to write a textbook for students.
Okay.
But it's very difficult to find time.
Maybe, I don't know if I say it, maybe after retirement? What are your plans about retirement?
I don't know. It's actually very soon. I think my retirement, I will continue working, but maybe not as stressful as it is now. But yeah, we will see.
Okay, thank you. So, any other questions from the audience? If anyone is interested to raise the last one question, one or two, or comment or follow up before we close. I know we had 2 hours of your time, Dr. Anne. Thank you very much for being with us. Someone raised his hand. We are about to close, but let's see Abrar if she has a question. Abrar. Abrar. Please, Abrar. أبرار. طيب في غير anyone else? Abrar, you can go ahead. You raised your hands. You can unmute yourself, please. Okay. طيب. رغد. Ragad.
Hello, Professor Laureate. You're such an inspiration. Well, my question is it normal to feel lost or unsure about what area to choose during as an undergraduate student?
I would say yes, and I was in this situation, absolutely. I was hesitating between math, between physics, and then different part of physics. So take your time to choose. Don't keep your possibilities open so that you are not going into direction and then you cannot change. So keep this open as much as you do. Take your time to choose something that you like.
Thank you, Professor Laureate.
Thank you. Thank you, Ragad. Please lower your hand, Ragad. Any more questions? Okay.
These were many questions.
Of course, I personally have many questions, but I don't want to take the time of the webinar for that. But maybe I should answer one question. I have been asked that questions many times during this period of distributing the announcement and arranging for this webinar. I was asked this question by my students and even by some of my male colleagues. Why Anne Laureate? Why don't you, for example, host Björn Agostini? But we know why, because she's a woman. And at that time I replied, no, it was not the reason. Yet, yes, I have been always impressed by Marie Curie and by female scientists who won Nobel Prize, including Professor Anne Laureate, but that was not my main reason. There were actually two reasons behind choosing Professor Anne Laureate among those who won the Nobel Prize in 2023. The first reason is that simply she was responsive to my emails. So my plan was I will try with this lady. Then if she said, no, I'm sorry, I'm busy, I would go to the second co-laureate. Then if he said no, I would go to the third. But I was very lucky that she was very responsive and very kind, very generous. And she said, yes, it would be a pleasure. The second reason is that in 2023, before the Nobel Prize announcement, I had the pleasure to spend 4 months in Lund, in Max 4, which is one of the scientific or the research arms of Lund University. And I visited Physicium and Lund University, but I didn't have the chance at that time, also I didn't know her at that time, to meet Professor Anne. This was in February until May of 2023. And the last period of my visit to Lund at that time, like these days, I had the chance to give a talk at Max 4 to Max 4 researchers and staff. And when I started my talk, I was super excited that I will speak to scientists about atomic physics on the land of Lund. And I started my talk by saying, it's very exciting to talk here about atomic physics in a university that is the home university of excellence in atomic physics. And I mentioned Rydberg and Carl Sagan. Months after, when the Nobel Prize was announced and I read about the atomic physicist Anne Laureate, I was also excited again, but I felt sorry that I'm not in Lund. And in that moment, I started to think about communicating with her, to host her, to let my student meet such a distinguished figure in physics. But I didn't do in 2023 because I expected that she will be super busy to answer my email. I did it in 2024, and then we started to organize for this event. So it was not because she's a woman. It was just like I tried. I started with the Women Fellow, and she was responsive, and she answered generously my email. So I didn't need to go to Plan B and Plan C and to try other laureates. So that's why the choice was to host Professor Anne Laureate. So
well, I'm trying to answer all my emails actually. Something.
I can imagine. I can imagine, and it's an opportunity to thank you really again for your generosity to accept the invitation from the University of Jordan. I would allow a last question from Nadine. She just raised her hands. Nadine.
Hello, everyone. Actually, I don't have a question. I just want to thank you, Professor Anne, for the beautiful and well-structured presentation. It truly shows how lucky are your students to have you. Thank you so much for that today.
Thank you very much.
Thank you, Nadia. Thank you. Thank you. I think we are about to close, and I would like anyone from LAMBDA to say a closing remark. Reem? Reem?
Yes, I'd like to conclude by profoundly thanking you, our distinguished speaker, for being here today. It's fair to say we're in awe not only of your remarkable intellect, but the path you've carved in the world of science. Your work in attosecond physics has opened a window to the invisible and shifted our understanding of reality, and it feels especially fitting to host you on this occasion of the International Day of Light. I'd also like to extend a thanks to LAMBDA team and Dr. Hanan Saade for bringing this vision to life, and to all of our guests for being part of this inspiring moment.
Thank you, Reem. I second on what you have explained, and it's a pleasure that we had Professor Anne Lollier with us this afternoon. Professor Anne, thank you so much for accepting this invitation, for being part of this afternoon, and we hope one day we meet you in person.
Yes, I hope that too. Thank you very much, all of you, and this was really very, very good questions.
Can we take a group photo before we close?
Yes, yes, please. All participants, let's allow cameras. If anyone interested to open the camera, let's take a group photo. I allowed cameras for all attendees. So if anyone would like to open the camera, please do. No, I did something wrong, maybe. No, they are participants are here. I enabled camera. So Reem, maybe you can take a group photo from your side.
Mm-hmm.
Syrian, other participants, please open your camera. Alia. Nobody open the camera. Please do. Okay, you can take a group photo from your side. You can try one, Reem. Reem?
Yes, I took two, actually.
You took two? You should say 1, 2, 3, photo.
Okay. 1, 2, 3. Okay.
Fine.
Yes.
Okay. Thank you again, Professor Anne Laurier. Thank you for the time, for the inspiration. Thank you so much.
Thank you very much. Bye-bye.
Bye.